Okay, so now can we extend this Bayes rule to the partition, which is again a very important extension, right? The whole concept of conditional probability and so on and so forth, right? So conditional probability extended to partition, the constant. Okay, so here we will say that, as we said at the start of this lecture, that AI is a part, right, the set AI collection AI is a partition of omega, right. Then we know PB will basically be a sigma of 1 to n P of BAI. This is exactly what I wrote earlier, right. Now I want to write these guys using conditional probability, right. It makes sense to condition on, in this case, let us say AI, because they are, it turns out that in most cases this AI, the partition on omega AI is the first stage, right, and B is something you observe in the second stage, right. So this becomes, using that here, this is P of B given AI into P of AI, PB given AI times P of AI, right. So sometimes this is also referred to as the total probability theorem, right, where you have the priors, right, the prior probabilities and some posterior probabilities and so on, right. So we have to be a little clear about the terminology here, right. Let me see if I have well okay. I even okay, so let's just do the maths first, right. The terminology I'm not right, let me brush it up before I come and say it here, right. What does the mathematics say about this about, for example, P of AI given B? That is clearly a posterior probability, right. That is, you observe that B has occurred, you want to calculate the P of AI given B, that you can do using Bayes rule, right. So clearly, yeah, now the P of AIs are called the prior probabilities, that is your assessment of the situation before making any observation, right. The probabilities that you have before any, right, without any additional information are the priors. The P of AI given B's, all of them, they become the posterior probabilities, right. So let me write it out and then, so what is P of AI given B? This is obviously P of AIB divided by PB, isn't it, by definition, right. And of course you assume that there is no problem dividing by PB, right. Then going back here, this P of AI given B, let me write this thing here again. So what will Bayes rule tell me? It's going to be clearly, if I want to express everything in terms of the prior probabilities in the conditionals P of B given AI, what should I do? I have to write this as P of B given AI into P of AI divided by P of B. This is one step. Then of course you can go to another step also. This will be P of B given AI to P of AI divided by, right, this expression for P of B. Sometimes it's conventional to write down all this. Now you have to be careful in notation, right. We have already used I here, so we should not reuse I. This I we cannot change because that is what, right, is running through the whole left LHS and RHS. So we have to change this I. So we will change it to, let us say, k equal to 1 to n P of B given AK multiplied by P of AK. So this scope of this integer k is only within this summation, right, the denominator summation. So there is no k coming outside. Anyway, so this is true for all I in 1 to n. So for any I you pick 1, 2, 3 whatever up to n, you can express this conditional probability like this. So this is saying how the posterior probability, so this is a posterior probability, right. What is, right, the changed likelihoods of all these events AI, right, knowing that some B has occurred. Again we will come back to examples later on, right. I want to do all this first and then examples we will take up next week, right. So this is the posterior probability, and I said let me just add the point here, this P of AIs, all of them are the prior probabilities. Just for terminology, right. And clearly, right, because it is a partition of omega, this summation of P of AI has to be unity. So if AI is a partition of omega, we continue with this point, right. This implies of course that sigma P of AI, the prior probabilities all add up to 1, there is no question about it. What about the posterior probabilities, P of AI given B? They also have to add up to 1. Is that obvious or not? That is obvious from here, right. Supposing I add up all these guys from 1 to n, will it not equal this? It has to equal this, right. So this follows from the original set of axioms we have. Further, here I will use I, right, because there is no problem, this is also equal to 1, which is what you expect anyway, right. Given that B has occurred, one of the AIs must have occurred, because the AI is a partition of omega. Always in any run of the experiment, one of the AIs occurs, it has to occur, right. So that does not change whether you observe B or not. So this is like a sanity check on this whole enterprise, right. So you have prior probabilities, right, which are independent of any observation, right. Again the wording is very important, right. You can write all pages and pages of maths, but ultimately it's your understanding of all this maths is what is bound by the English, right. So don't underestimate the importance of the wording to explain the maths. So why is this, so what are we saying here? We are saying that we have a set of probabilities AI, right, which are our first guess in some sense, or first estimate of likelihood of those AIs, right, before any observation is made. Then you make the observation B, that can significantly change, right, our likelihood, the way we think of the AIs. In particular, right, if some of these AIs do not intersect B at all, then what happens? The posterior prior probability can be some positive quantity, but the posterior probability will be 0. Okay. So it is important to always be able to look at the significance, the verbal significance of what we have written out using mathematical notation, right, and that is especially true in the subject of probability, right, because these quantities, probabilities are very, sometimes they are fuzzy to understand, they are sort of slippery things, right. So at each point I will try my best to make sure I bring out the English also, okay.